In this lecture, we'll cover the concept of rolling with slipping and also the pure rolling. Now, let us first understand what we mean by pure rolling. If this is a circular or a cylinder, circular body, a cylinder having omega as the rotational speed and r as the radius and the speed of center of mass bv. So for pure rolling, V will be equal to omega R. Means if you look at it like this, if omega is the rotational velocity and if no slipping is taking place, so because of this omega, the center of mass will have velocity equal to omega R. And if this omega R is equal to the velocity of the center of mass, the velocity, actual velocity of center of mass, then it is a case of a pure rolling motion. But if omega r is not equal to velocity of center of mass, then it is rolling with slipping. Now it can be in two situations where let us take omega r is less than v center of mass and case where omega r is greater than v center of mass, where when this is unequal, as we said, slipping is taking place, but this slipping is again of two types. Now for this situation, v center of mass is here and the omega r is less than v center of mass. It means that it is slipping in forward direction, where omega r is not able to give it the enough omega r is not able to give it the velocity which it should be giving to the center of mass to have the velocity equal to vcm for the pure rolling. So here it will be slipping forward and the frictional force will be acting on it in this direction. And in this case, where omega r is greater than v center of mass, then it is slipping like in the backward direction and the friction force will be forward. It is the v center of mass. So omega r is greater than v center of mass, so it will be slipping like this. So the frictional force on the body is in the forward direction. Here the frictional force is in the backward direction. Now once we have this situation, we can draw a graph to easily understand it. Here we draw v center of mass and we find the location of omega r. The motion will be in such a way that v falls and omega r rises until a point comes where pure rolling starts. And let this be the time. So omega r will be rising and v center of mass would be falling. How that happens? Now see, the friction force on the body is backwards, so it will oppose this motion of the center of mass. The initial velocity v center of mass has to fall because of the opposing frictional force. Let the final velocity be v final. So v final is equal to v center of mass, which is initial, minus a into time elapsed. And what is the value of a? Will be the frictional force which is acting on it divided by mass of the body. Now look at the angular velocity. This is the initial omega r and let be omega final r, where omega final r becomes equal to v final. So omega is increasing here and you can see the frictional force which is providing torque is in the same direction as omega r, as the omega. So omega final would be omega initial, which is there, plus alpha times t. And what is the torque? Torque is equal to F into R is equal to I into alpha. So alpha is Fr upon I. So omega final is equal to omega plus Fr upon I into T. Now since omega final into R is equal to V final, so we multiply this by R, this whole equation, we get R omega final is equal to R omega plus Fr square upon I into T. This is nothing but V final, and V final we got by this relationship. So we can equate these two equations and we'll finally get the value of time. So this is V final, which is V center of mass minus F upon m, which was acceleration, into T, is equal to R omega plus Fr square upon I into T. You can solve this and you get the value of time at which the pure rolling starts. Now similarly, we can deal with the situation of other case where the omega r is greater than V center of mass. So in this second case, this was the first case and this is the second case. I am redrawing the second case again, where omega r initial is greater than V center of mass. And in this case, the frictional force will be in this direction, this V center of mass. Now draw the graph again, and this time omega r happens to be greater than V center of mass. This is the initial position. Omega r starts falling, V center of mass starts rising, and a point comes at a particular time when pure rolling starts. This is the point of pure rolling. You can see V center of mass is increasing, and here also you get the logic. The force is in this direction, the acceleration is in the direction of velocity, so velocity has to increase. The final velocity would be V initial plus acceleration is force upon mass into time t. Similarly, we can write for omega final r, and this is V final. They both are equal at this point of time. Omega final will be less than omega, because you see the frictional force is giving a torque which is Fr and which is opposing the omega. So omega final would be omega minus alpha is Fr upon I, as we have found previously, into time t. You multiply this by r, you get R omega final is equal to omega r minus Fr square upon I into t. This is nothing but V final, and V final has this value, so you can equate it. V center of mass plus F upon m into t is equal to omega r minus Fr square upon I into t. Solving this equation, you get the time t when the pure rolling starts. So it is this kind of question can be done very easily if you draw this kind of graph to begin with. It makes you understand, like if I repeat it again, if you try to see, suppose you are not able to make out in which direction the frictional force has to be taken. So to do that, a very simple method is, if you are given some omega r and V initial, and you are not able to, even if suppose it is greater or less, whatever, you are not able to find out in which direction the frictional force will be, just look at this graph. Suppose Vi is greater than omega IR as per the values given. So Vi will be here and omega IR will be here, and finally they have to join because the pure rolling has to start after this time t. This is the pure rolling point. So velocity is falling. It means the friction force is acting against the motion. So this will be the friction force if this is the V initial, and even if this is the omega initial. So where V initial is, wherever V initial is greater than omega initial R, the friction force will oppose the motion, the translational motion, but it will aid the rotational motion so that omega I rises. So by this graph you can easily, first if you draw this, you can easily find out what is the direction of frictional force which you have to take, and then solving the problem becomes much more easier. I'm just showing it again. Omega I and Vi, multiply this by R and then draw the graph. Suppose now you have omega IR is greater than Vi. So omega IR you draw here, Vi you draw here, and they have to ultimately meet at a point where pure rolling starts. This is the time t when the pure rolling starts. This is the pure rolling point. Pure rolling point. This is moving downward, this is moving upward. See, the velocity here is increasing, so the frictional force in this case has to be taken in this direction, and the torque you can see is now opposing. The torque, which is Fr, is opposing the rotational motion. That is why the rotational speed is falling. So by this principle you can solve such problems by this graph and applying this formula. Thank you.